Alright, hello everybody. Today I will be showing you how you can go from a schematic that you already have made to a PCB from scratch. Now everything in this video also applies if you're just doing a respin of a board, but for this video I'll be using the RPi hat, which doesn't have a PCB yet, so I'll show you how to make it from scratch, but once again, all this can be applied to if you're just doing a respin of a board too. So before you actually start the PCB portion of your project, you kind of want to annotate, you want to re-annotate your schematic. And what that means is like fixing all the designators. Now, a designator is this little number that you see above each component, and it's kind of just like the identifying number. So like U6, C22, D1. Sometimes when you put a new component in, it'll just say like R question mark or U question mark, depending on the component. So that just kind of means like afterwards you have to go through with Altium and automatically fix all these designators. And to do so, you go to this tools menu and you go annotation and hit annotate schematics. It'll open up this panel, and then from here you can update all of your. You hit update, it'll update all these annotations, or you can hit reset if you have issues with that and re-update them all. It'll do all this stuff for you, but you can also go through and manually do it if you wanted to. When you're done though, you hit accept changes, and it'll show you what it's all doing. It's kind of switching any of these question marks to assigned numbers. And once you hit execute changes, you will see that also it'll show you if you have any issues with your schematic here. But you'll see that it'll go through, there wasn't any wrong here, but it'll go through and re-enumerate all of these designators. All right, so now that you've annotated it fully, you can go through and add a PCB file to your project. And to do that, you right-click the name of the project and you go add new to project and then PCB. And usually we just name the PCB file the name of the board. So it'll generate this just blank PCB, and hit Control S and save. I'm just going to call this RPi hat. And now in your PCB files, you can view them in three different ways. The first is just this board stack mode, which like I don't really use this one very often, but the second one is where you can see the actual routing and the traces, and the third one is just a 3D view, and you can see this is just a blank PCB right now, so it's just a square right now. So before we actually get into like putting any of the components on, I kind of want to show you how you can resize this board and make it any shape that you want it to be. And to do that, we're going to create a board outline, and what that is just like you're making a shape to then define the board shape based on that. So for example, if we wanted a rectangle, you can come over here, you select the rectangle, and you gotta make sure you're on the mechanical layer. So down here you have all of your different layers on the PCB. So if we go to the mechanical layer, you can make whatever shape you want. Let's say we want just a rectangle, and if you select this rectangle and go to design and then board shape, you can define board shape from the selected object. And what this will do is it'll make this board the shape of the rectangle. Now you can manipulate this to do any shape that you want. You'll see some of our boards are not always just straight rectangles, or we have curved edges sometimes. And if you're wondering how we actually do that, I can quickly show you. But we kind of do this line tool, and we go about creating a shape. It doesn't have to be perfect, and you'll see why I'm doing these kind of corners in a second. But go about like this, and then we take this arc from edge, and you can come over here, and if you hit space, it'll actually flip this arc, and then you can connect it like so, and then delete this line, and then you would just go and kind of copy this arc and paste on all your corners. So you can really kind of just make any board shape you want, but you have to make sure you have a board outline layer. Altium doesn't make that by default, but it's very important that you do that. Actually, I also want to show you how you can kind of copy and paste on this. It's like you have to, when you hit copy, you have to choose a reference point of where you're copying from. So when you do Control C, like a little crosshair type of thing pops up, and you select kind of a reference point on where you want to copy this from, and you'll see like when I hit Control V, I'm moving it based off this reference point. And if you hit spacebar, obviously I picked a really weird reference point here, but if you hit spacebar, you can rotate it just like that. So that's how we can go and paste them all on all corners. All right, so now that we have this board outline, we can actually go through and update all the components and transfer them over from our schematic onto this PCB. So if you go to a schematic page and you hit design and update PCB document, it'll pop up with this change log kind of, and you go through kind of how we did earlier and validate all the changes. If you have any errors, you'll get some messages, and so try and resolve all of them. Or you can, up here, if we show these, it'll show all the errors. I'm just ignoring this error for now. Oops. If we hit execute changes, it'll probably warn me about these errors again. And then we should, as you can see on the PCB, it goes and it basically pastes all of our components. And if I go to the 3D view, you can see that it's just taken all these components and placed them on the side of the board for us. And we can then get into placement. Now, placement is a very, very important, it's probably the most important part of like PCB design. It's like 80% of the work is placing the components right, so that you can make routing and making the traces easier. So I would say very much take your time with placement. One thing I always do, and I very much recommend it if you're starting off new with placement, is open up another design, look at it, like kind of learn about why they're doing designs in such a way, and try and mimic those type of patterns that you see on your board. But a high level, for example, if you have a connector like this LEMO connector, it obviously you wouldn't put this in the center of your board. You would put it on the edge so that you can actually plug stuff into it. But one thing you'll notice is when you're kind of doing all these placements. Also, don't mind my computer being very slow. It's because I'm recording. But you'll see we have a Silkscreen layer, which is basically the layer on the top of your board that has the writing, the paint almost, right? And when you're doing any kind of work in PCB, a very helpful thing to do is open your layer manager, which is just by double clicking this, the current layer you're on right now, down here. And you can see it shows you all the layers of your PCB. So when I'm placing or when I'm routing in general, I like to just hide the overlay layer, which, as you can see, removes all the text that's on the traces on the PCB, and it allows me to kind of like fine tune and place things without having to worry about the overlay right now. Obviously, that's something you have to go do later down the line. But definitely when you're just working on placement and doing routing, I would hide the overlay. One thing that you should also do if you're starting with a new PCB, this doesn't apply if you're doing a respin, but you want to make sure you're importing the correct rules in Altium. So kind of when you have a PCB project, you set certain rules like how distances can be for traces and with thicknesses of vias and minimum thicknesses and certain design rules. And to do that, you can the easiest way, at least the way I do it, is I just kind of import it from an existing board. It's quickest that way. And to do that, you can just go design rules. And then if you just right click on design rules here, you can click import rules. And if you just hit OK, Control A to select all the type of rules. And you can then go to a other project you have in Altium. And if you've exported the rules from there, just doing the same way by hitting export rules, you can go do that on a different project. And then after you've done that, you can hit import on your new project and import the new rules in. So make sure you do that if this is a new project that you're starting. But if this is just a respin, then that doesn't apply to you. So one thing you'll notice is like there's these lines that are going everywhere, and these are basically guidance indicators to what pads need to connect to what. So I placed these two capacitors here, and you'll see like they're both the same net, P3V3B, and there's a line connected to the two of them, which means like they need to have their nets connected together. So if you hit Control W, you will start like your trace drawing, and you have to be on the right layer. So as you can see, this pad here is red. It means it's on the top layer, and then you have the bottom layer, and then on certain boards we have like multiple signal layers in between too. So I'm going to go to the top layer here, and also you can shortcut. You can do Control Shift and scroll wheel to like go between layers. But so on the top layer, I can select the middle of this pad. You'll see a little circle will come up, and I can draw this trace and then connect it to the other pad. Also, this is a very bad trace. Don't do like this. You have to make sure you should keep it like straight like that. But yeah, that's kind of how you know like how to connect what paths together is you use these guidance lines. So in general, there's kind of two ways you can go about making these connections. The first is with traces, and the other is with polygons. And I kind of want to go into detail about like how when you use these two different types. And to do that, I'll open the LV controller from last year, so I can kind of just show you examples on where we use them and why we use it this way. So the first is the trace, which I just briefly drew one earlier, but I will kind of show you by redoing one of the traces on this board. Um, so let me show you on this CAN2 trace, for example. So I'm going to delete this, and like I said earlier, it's really messy. It's hard to work on this when you have all the overlays on. So I'm going to close them, making it much easier to work with. And basically, the hotkey, like I said earlier, Control W to draw a trace. And if you start it here, whilst you're, so first thing you'll notice off the bat is the trace is very thick. So if you hit tab, it'll kind of pull up this pause and it'll free your cursor. And you can change the width of your trace down here. So let's say I wanted, I don't know, 0.35 millimeter trace. You can see it changes the width of that trace. And if I resume, my cursor is connected to this trace still, and I can route this however I want to route it and connect it to, CAN2 eventually. The other thing is you can do Control Shift and the scroll wheel to go up and down layers. Now, this is very useful when you kind of, like this board is multiple signal layers, and if you have traces that are traveling around and they're kind of intertwining, you have to be able to go up and down traces. So this is where it kind of turns into like a bit of a video game sometimes. You want to see how you can get from point A to point B most efficiently. So that's when you can kind of use the advantage of like going on different layers of traces. So for example, if I'm on the top layer, I can do Control Shift, scroll wheel down to, I don't know, the blue layer, and then come back. Maybe I'll go to the bottommost layer, and I can come up here still. In general, though, you kind of want to minimize your distance of the traces, and you also want to play with the thickness of it. Now, you're probably wondering, like, how do you know what thickness of trace to use? And you can actually calculate that with a tool called PCB Toolkit. This is like very important, especially for the HV team. You kind of have to make sure you can correctly spec out all of your traces, and this is a tool that kind of allows you to input all the parameters of your board and like maybe how far your trace is, the current that's passing on it, and it'll kind of spit out the minimum requirements for thicknesses. I'm not going to get into this tool too much, but generally the way it goes is signal traces are always very thin just because they're just enable signals like high low, but usually when you have power rails like for example this 5-volt rail, this 5-volt trace is much thicker. The other way of routing is using polygon pores. Now these are a bit more like difficult to wrap your head around, but once you get the hang of it, it's very straightforward. But polygon pores are used when you kind of have a grouping of pads that you want to connect together. So I've placed these 4 components here, and as you can see, they all have a P5-volt net. Now I could go through and use a trace to connect them like this, but you can see like it wouldn't be the best way of doing it, nor is it clean or efficient. So the best way is in this scenario here is with a polygon pore. And if you come up here to this menu icon that says Place Polygon Plane, a polygon pore is basically a custom trace that is a shape of some sort. So I can go through and draw a rectangle around this 5-volt. Let me move this over a bit. But I can go through and draw a rectangle that surrounds this grouping of objects. And once I click off of it and select it, I can open up the properties panel here, and I can basically assign it a net. So I want this to connect to all of the 5-volt pads that it's touching, right? So then I would come over here and select type in P5 volts, and then report it, and you'll see it basically uncovers all of these 5-volt pads. Now this is obviously a very basic way of explaining it, but there's so many use cases to this. Also, a very useful tool is the Polygon Manager. So if you hit the shortcut is T, G, and by the way, if whenever you open up like a menu, you see how one letter is always underlined on each of these options. That's how you can just press that key and create like a shortcut for yourself. So when I hit T, it's opening up Tools, and then G is opening up, where is it? Polygon pores, and then M is opening Polygon Manager. So if I want to do it quickly, I can just do T, G, M, and it'll open this Polygon Manager. Now, what this is just like an area where you can see all the polygons that you have on this board. Now, obviously, I've just only drawn one, but when you have a lot, you kind of want to sometimes hide some of them or show some of them. This is kind of your go-to panel for how you can manipulate them. So if I open the LV controller, and I once again do T, G, actually, let me really quickly delete all these traces that I was doing. Yeah, so if I do T, G, M and open the Polygon Manager again, you'll see on the LV controller there's quite a few of them. Now, since I was showing you guys I was talking about tracing earlier, so I shelved them all, and what that means is just kind of hide them. So let me actually unshelf all of them, and to do that you can, the command is TG and then restore. So if you select that, it'll kind of, I'm going to report them too. So if you show all the polygons on this board, this is what you see. And this is kind of when you open an Altium project and go to the PCB, you'll notice this, and I can show the overlays again. But you can't work on this board with all the polygons showing, which is why the whole concept of shelving is there. So you hide some of them so you can work on other parts of the board. So if I open the Polygon Manager, I will get rid of the ground pour on this board. Now, on almost all of the LV boards, at least for sure, we always do a ground pour on the board. And what that is you'll see all these components most of the time they have a ground pad, and we want to make sure, like, you could connect all these ground pours, these ground pads together manually with traces, but you would have kind of high impedance. It would cause some EMI, like electromagnetic interference issues. But so what we do instead is we do a polygon pour, where we kind of just like make a massive pour of the entire board that is all just ground, and we do this on every single layer. So as you can see on one of the layers, here I'll start at the top, but the top layer has this big massive ground pour, and this is basically connecting every single ground on the board together. So I'm going to go through and shelf this one, and then also on the second layer there's also another ground pour. I'm going to shelf this one. On this layer too, there's a ground pour. I'm going to shelf this one, and you can, by the way, down here you can see what this polygon pour looks like. And then lastly, on the bottommost layer, I'm going to shelf this ground pour. And once I hit apply, you'll see that I can now see the board again, which is this is why I did this earlier, just to make this a bit more easy to understand. But you can see these are all of the polygons now that are not ground showing. And as you can see, they're used all over this board. It's a very, very useful way of routing. And just to go through some of these, you'll kind of get a better idea of when you would use them. So as you can see, we have these ICs. If I once again hide all of these polygons, shelf TGH. If I hide all these, you can see this IC has a whole bunch of 24 volt pins, 24 volt, 24 volt. Same thing with these. These are high side drivers. They all have 24 volt pins. It wouldn't make sense for me to manually connect all of these, right? Which is why we can use a polygon pour to connect all these 24 volts together. So let me restore what I just hid there. And as you can see, we have this massive 24 volt net that stretches across all of these. Whoops, where did I go? I disappeared somewhere. And I have this massive 24 volt polygon pour that kind of stretches across these three high side drivers. It's also over here on some other signals. And you can, once again, you can do these on any layer too. So this 24 volt layer uses vias to drop down to a bottom layer and continue throughout the rest of the board. And if you're wondering why here we have like 9 vias instead of just like 1 to drop the top layer to the bottom layer, these 9 vias are there because it's a very thick trace, and it wouldn't make sense to have all this current pass through one small via to get down to the bottom. So what we do is, since the shape is so big, you can put 9 vias together to connect the two boards. Also, I feel like I probably should have clarified what a via is. A via is kind of just like a through hole to drop between layers. But yeah, so some other places where this is used, for example, once again, if I GGH and shelf all of them, you can see there was a lot of motor controller signals here together, and these are aligned in just so that we could use a polygon pore in this situation. So, which is why we have one giant polygon pore that is the motor controller power net. Once again, if you hit properties, you can see the net and change the net like this, how I did earlier. And I guess like one of the the biggest one here is you can't miss it, is the massive 3.3 volt net. So on the STM32 we have a whole bunch of 3.3 volt pins. You know, everything coming out of the STM is always 3.3 volts. So we use this massive 3.3 volt polygon pore around this area to kind of stabilize all of these 3.3 volt pins. And if you're wondering why this is done on the third signal layer, this is just a design choice. Like how it would be a lot more difficult to, if you had this on the top layer, it would really much like interfere with every single pin on this board. It would be cut out really weirdly, and it would make routing a pain to do. So that's why we kind of, everywhere you see a 3.3 volt, it sticks out of this pin and then drops to a via to connect to this massive polygon pore. So I guess that's kind of the general gist of routing. Obviously, it's a lot more difficult than the way I explained it, but the best way to do it is just by trying it out yourself and looking at existing designs. But usually once we finish routing, we kind of toggle the overlay back on, which I have it on right now, and you kind of fix all of your Silkscreen. And what that means is, like, you have to make sure all these component designators are like visible. None of them are kind of on top of each other. And then we also go through and we put the sponsor logos, or the Canadian flag. We put the Altium logo, and or the board title, kind of the finishing touches for the Silkscreen we add on. And what else? We also, you'll see there's via stitching on the corner. And what via stitching is like, you just have all these are individual vias, and it's kind of there for like structural purposes. You can kind of imagine it as like if you had a stack of papers and you like stapled the edges of all of them together. It's not like required, but it is helpful for when the PCB is manufactured. These are also just like placed manually. It's quite the pain to put them in, but has to be done. And what else? You'll see on the corner we have like these mounting holes, and this is literally where we just like put screws in to mount the PCB to whatever enclosure it's in. And to add these, I can show you. You can go to the RPi hat. I already put one here earlier, but if you go to our components and you search M3, you'll see M3 mounting and place component. You just put these on the corner of your board. What else? At the very end, we also usually add what is known as teardrops. And if you look at where all these traces are, on the corners of them, you can see that they're kind of rounded. This is different than when you're like routing yourself, and you can see it's just like it's a straight, sharp angle. So what this curve thing is a teardrop, and you can just go through at the end. Once you're done all of your routing, if you go to design, it is here we go, tools, and then teardrops. You go, select for all, like across your entire board, and you hit OK, and it'll go and it'll apply this teardrops on every single one of your connections. There is actually one last thing that I want to talk about, and that was thermal relief on like through-hole components. And basically, a through-hole component, by the way, is just like any component where the pin goes through the board. So if I go into 3D mode here and I use Control F to flip the board, you can see like these are all through-hole components because the pins go through the board. And basically, if you look at this pin right here, you'll notice that like it's on this GLBMS out net, and it's connected to a Polygon port that is also that net. But you'll notice that like around the edges of this pin, it's not like fully connected. It's only connected in 4 regions, and that is because of thermal relief. And the reason why we do this is quite interesting is because like when you're soldering this capacitor on, and I'll go back to the my computer's really slow right now. But if I am trying to solder this capacitor in, right, so I'll put it through the through hole and I'll start applying solder here. But to do that, I have to kind of like heat up this portion of the pad, right? But you'll notice that if I put the solder there, it won't be like heating up. It won't. It'll take a long time to heat up, and like our soldering iron almost just won't have enough heat to melt any solder there. And that's because it'll just be pouring all the heat of my soldering iron will just be dissipated into this polygon. Because it's a big surface area, and if I'm just heating up this pad here, it would just the heat would just dissipate straight to this polygon port, and I wouldn't be able to solder the component on. Which is why we do this thermal relief. And we kind of like only partially connect this pin to this polygon. And to do this, I can just show you like on this pin, for example, you just click it and open the properties tab, and there's a check mark here that says thermal relief. Check that off, and then click on this direct, and it'll open up like the options of what type of thermal relief you can do. And then just select relief connect. And I believe if you have your rules imported correctly, all these should be set to the right values already. And you just hit OK, and then you have to re-pour the polygon that it's attached to. So polygon action, and re-pour my selected polygon, and you'll see like now there's thermal relief on this via. But we would never do this because this is just a via. You're not actually like attaching any component to that, so there's no need to. But yeah, at this moment, I can't seem to think of anything else that would stop you from getting started on designing your PCB. But just to reiterate, like you always want to do your placement first. That's the most important part. You should spend like usually most of your time is on placement, kind of just like thinking through and visualizing how you want to connect components without actually routing them. And then you go through and do your routing, and then at the end you fix up your silk screens and adding all these final touches like copper thieving, via stitching, teardrops. You do that stuff all at the end. But as usual, feel free to reach out if you have any questions, and good luck.